So we have looked at, bring it back in. We have looked at how to solve basic differential equations, right? Where we have dy dx equals x plus 2 or something with an x in it, yes? Now we're going to have things that are a little bit more complicated, okay? But the basic idea of them is still the same. So remember, what are our solutions for differential equations?
Functions.
They're functions. So you're not just going to get some number. So it's different than when you had like a quadratic and we were solving, or some other type of equation, because you would solve and we would get a number. Here, our solutions are functions. And remember that we can have both general solutions, which is where we still have our c's and k's or things like that, or we can have particular solutions where we have to plug stuff back in to solve for our c values. But our first step is going to be to rewrite y prime as dy dx if needed. So sometimes it will already be given to you with dy's and dx's so that you don't have to worry about it. But if you have y primes, you have to have those dy dx's in there. Then we're going to separate dy and dx to opposite sides. How have we done this in the past? Yeah, so if I have dy dx, I can multiply both sides by a dx, okay? Sometimes we might already have an equation where my dy and my dx are already separated, and we'll look at how we deal with that. So this is the part that's different, okay? Because we've dealt with a lot of this up until now, but now we're also going to have to move corresponding variables to the correct side. So that part is a little bit different. We will then integrate both sides.
Seems like a lot algebra steps.
It is. Because then lastly it's to solve for y and slash or c as needed. So we're going to look at different ones. So if you are not given an initial condition, you will not solve for c. Your c will just be in your final solution. Okay? Sometimes we will solve for y, and we'll look at some where we do that. Sometimes we will not solve for y. Okay? And we'll look at why we don't want to solve for y in some of those, because it would not be fun. I will tell you that I'm pretty sure I gave you a foldable on these, but it is going to be helpful to remember your exponent and log properties. So when we did last first semester, we got a nice little foldable on those.
I like those.
That's good. Hopefully you still have it, because we're going to refer back to it. Yeah. So, then what's our next step? Integrate. So what is the antiderivative of 1 over y dy? Absolute value of y plus c, okay? But what are we also going to get on the right-hand side? A plus c, okay? So if at the end we subtracted the y constant and we had like c1 minus c2, if I have a constant minus a constant, what is that still going to be? A constant. So we're just going to pick one set, doesn't matter which one. Usually we tend to do it with the x's. And we're just going to put one constant over on that side, and that's basically going to scoop up all the possible constants. Because otherwise you start dealing with subscripts, and you don't really like those. So, are we okay with that? So you still have to have a plus c, but it only has to be on one side. So then what is the antiderivative of 2? 2x. And then now we do have to put our plus c. We're okay with that. Now, I did not give you an initial condition, so we do not have to solve for c. However, what do we need to solve for? The y value. Where is the y right now? In an absolute value in a log. Okay, how do we undo logarithms? Exponentials, okay. And what's our base for a natural log? No, that would be like a common log. So it's where we don't have a base. What is it? It's an e. So what do we do with our exponentials? Yeah. So we remember it's called exponentiating. We put both sides as an exponent of whatever our base is, which in this case is e. So then what are we left with on the left-hand side? Yes. But for the most part, we'll go ahead and we'll think about this here. Okay, we'll put absolute value right now. And then we'll talk about why we don't need it here in a second. Alright, next up, what do I have on the right-hand side? Plus c. Okay. Now, there's nothing wrong with that. However, we don't tend to like that because we don't like our exponent to have addition in it. But let's think too, back to those things I said we're going to think about, our exponent rules. Okay, if I added in my exponent, okay, what did we have to do? What operation did we do to get addition in our exponent?
Multiplication?
Multiplication of what?
It's like the Pythian base
Okay.
with the exponents that are like being added together
Okay.
on each of the bases that are being multiplied together.
Okay. So group 2, what would that be instead? Okay. I'm gonna rewrite my e to the c first. Okay. Now, group 1, what is e to the c going to be? Just like e to the c. C is a what?
Constant.
So e is also a, yeah, so e to the c will also be a constant. Alright. So we're actually going to drop the e to the c, and we're just going to say that the c e to the 2x. Which is why when we were solving, like verifying some solutions, our c values ended in front, and it's because you had stuff where c's were in your exponents, and we like it to be multiplied to the front, because it makes it easier for us to solve. Are we all with me there? Now, the reason why I said that technically we can drop our absolute values, so, how do we drop absolute values? We just talked about this on our homework.
Separate it into positive and negative.
Right, we would have a plus or a minus, yeah? But if I have a constant, if it's a positive constant, is it still a constant? If it's a negative constant, is it still a constant?
Yes.
So basically we let our c kind of like absorb that plus or minus. And the way you would pick if it's a plus or a minus is if they gave you an initial condition and you plug that back in, if you ended up with the positive c, then you would put the positive c. If you ended up with the negative c, you would put the negative whatever number you had there. Yes? And we tend to do that like from the beginning. Like we'll drop the absolute value from just whenever we start exponentiating. Yes? Now, if you went ahead and wrote something like this one for a free response question, that would be fine. Okay? If you left it as e to the 2x plus c. Now, the only thing you would have to be careful about is if they gave you an initial condition, okay, you would be solving for a c that's in the exponent. Does that make sense? Which is a little, it's not hard, but it is a little funky at sometimes. However, the AP test and me, when you're dealing with multiple choice questions, is going to simplify it and write it with the c in the front. So, you at least need to know that the c can go there.
If it's FR2, could you still simplify just a little bit further?
Oh yeah, like if you simplified it all the way to down here, that's fine.
What about 2 steps below that? Like,
Here?
yeah, there or any of those in between.
Yeah. They wouldn't count off.
Okay.
Like I said, the only reason why the y equals c to e to the 2x is easier is like if you start trying to solve for c, it just makes your life easier. When I start trying to plug an x and a y in, because then you're not worried about taking the log of both sides in order to solve for c. Yes?
So did we just make BC just become C because we both don't know their values, but we know that they're numbers and...
Well, we know what e is.
I thought you said it's constant.
It is a constant. But like e is a constant. Like it has it's like pi. E has a number, like decimal associated with it, right? So no, we don't know what c is, but we know it's going to be a constant. So if I raise e to the first power, that's still like a decimal. If I raise e to the 50th power, that's just some decimal. Yeah, so it's just still some constant, no matter what we plug into that c value. And mathematicians like simpler equations to deal with. So is e to the c and this c the same constant? No. Technically, we could put like c1 and c2
That's
here.
what I was thinking. Is like,
But we don't tend to do that for our notation wise, because then you just end up with a bunch of subscripts.
it's just...
And at the end of the day, when we solve for our initial condition, we're just going to put whatever number is here. So it doesn't matter what e to the c ended up being, because that would be the same number when I solve as whatever this is. Does that make sense?
Yeah.
So yes, it is. It is a little bit of like math magic, yes, because this e to the c is just like go away. But yes.
It's absorbing all the constants.
Correct, it does. It absorbs all the constants. It's like the... Now, I will say, like, some people like to do, like, a lowercase c up here, and then they do, like, a capital C up front to mean, like, oh, that's the final big C, if it makes you feel better.
If you have good handwriting,
Yes.
you can do that.
Alright, other questions? Want to look at another one?
Wait, so we just end with that last answer?
Sorry, what?
So that would just be like the solved solution? Like
Correct, because they did not give us an initial condition, so our C value is going to be a part of our answer. It'll just be a general solution in that case. So, do we have our dy dx this time? Yeah! What do we need to do next then?
Take the C over dx over.
Correct. Now this time, are all of our variables where they should be?
No.
No. What do we need to do?
Move the y over.
We do not want to move dy over. We need dy and d.
Move
Oh.
the y over.
How so?
Divide both sides by 1.
Okay, so we get...
dy over y equals
Yeah. I would probably write this
dx
1
over
over 1.
2x plus c.
I mean, you can. I tend to not like to write our dx's and dy's as a part of our fractions, just because that tends to confuse y'all more than not. So, but yes,
Definitely confused.
Yes.
How do you know that?
yes. So now this looks a little bit more like what we're used to seeing with our antiderivables. So that left side should look very familiar. What is the antiderivative of 1 over y?
Natural log of minus 2 y.
Cool. Now, what does the right side almost look like? or in the bottom. Yeah? So it looks close to a natural log. But what do we have down there as well?
C.
And
Two.
2. The 2 is actually more important than the C is. What do we need to do then? U sub. So that's why we cover our integration techniques first, because all of those still apply as we are solving for our differential equations. So what is our du? 2 dx. Do I have an extra 2? No. So what do I need to do with that?
1.5.
Make it a 1/2 with my du. So we would have 1/2 times the integral of what? 1 over u du. And what is the antiderivative of that?
Natural log U.
Almost.
Absolute value.
Absolute value of u. Plus c, yes? Now, I went ahead and did that work over to the right-hand side because notice that if I put it in here and I wrote each of those steps out, you would also still have to write the left-hand side each time that you did that, right? Which is why I just kind of do it over to the side so you don't have to, because then we can just say that this is 1/2 times the natural log of the absolute value. What was our u value? 2x plus c, okay? But is that c the constant that I get from integrating?
Yeah.
No. So what do we still have to have?
Plus C.
Yes. However, this time, since I already started with the c, and that c value represents something that I started with, yes? And my constant of integration represents something that I get after I integrate. Those two c values are different, yes?
So C1 and C2?
We can. Most people tend to not like subscripts. So if you're okay with subscripts, you can put C1 and C2. However, the other way to do it is to put a plus K instead, which most people tend to like more, just so you don't end up switching your subscripts or accidentally putting the 2 too far up and then it just looks like C times 2, things like that.
But what happens when you get to your third C?
Then you would probably need, well, I mean, you could use just another variable, F,
Like plus
G, H, whatever you
plus
want
A
it
or
to
something
be.
like
What
that?
about the 8 C?
When you start getting that many, you're probably dealing with a pretty complicated thing. So then, yes, at that point, you're probably dealing with C1, C2, C3, and so forth. Because at that point, it's easier to use subscripts.
And
Yeah.
you also probably can like factor some of them out and like combine them.
Probably so. It depends on the question. Alright, now, does this look very nice? No, not really. So what might I do to solve for y? What was our word?
Exponentiate.
Exponentiate both sides. So on the left hand side, we're gonna have a y. On the right hand side, what are we gonna have?
E to the stuff.
Can I do anything within that step to make it a little bit more simple?
You can turn the half into an exponent, I think.
We can. What else?
You can say plus K.
Okay, so that would just become
K.
just a k in the front. Yes?
Oh yeah.
Okay. So then, yes, I still have e to the stuff, but I also heard, yes, I can rewrite, remember one of my log rules, if we don't remember, is if I have a times log base b of x, remember that we can rewrite any constant as an exponent. And what is a half as an exponent?
Square root.
Square root. Now, do I need the square root of the absolute value of that stuff?
Oh no.
Why not?
Because the square root makes it positive.
Well, it doesn't make it
Well,
positive.
it ensures that it's
It ensures that it's positive, because the only way for it to work is if that stuff is already positive. Yes. So we're looking a little bit nicer. Now what can happen?
Wait, we can do more?
You can. What is e to a natural log?
We can.
It's cancels out.
It reduces, yes, because those are inverses of one another. So then I just have k times the square root of 2x plus c. And now it's a much nicer answer.
Oh, much nicer.
It is much nicer than dealing with two natural logs, a
Okay,
1/2,
okay.
and two sets of absolute values.
Maybe.
Yes, that's much nicer.
Relative, yes.
Natural
By itself,
Yeah, but
no.
I mean, honestly, I hate I too. I is just no.
Alright. Do we have any questions on that one?
Are we gonna have to do this with imaginary numbers?
Do you ever have to actually use imaginary numbers in like normal calc
Get
stuff?
everything quick before you like jinx it.
In what? What is normal?
Like, just like calc 1, 2, 3. Do you ever have to use imaginary numbers in that?
Calc 1 through 3. Calc 1 and 2, you do not. 3, you start rotations, but I don't think you would be extending your plane any. It might be just Calc 4, where you start looking at two different variables. So.
But what are they even used for? Is like you touch something algebra 2 and then
Like intermediate calculations, where you can simplify a lot of like math stuff, sort of. Because a lot of the times you can like sort of get to the eyes and then like get rid of all of your eyes, and then get like no.
I don't ever remember.
Usually when we use them is when we're looking at two things that have a kind of what you would call like a third dimension. So if you're going to be like an electrical engineer, they are used a lot in electricity currents because you have both a positive and a negative current, and so those currents are going opposite directions, and so your imaginary I part. So remember, it's like A plus BI. The B part represents one of the currents.
So we're not gonna have to find imaginary.
No,
solutions.
not in this class. All right, we're not doing that one.
Oh, we're playing checkers.
That's good.
All right,
Yeah, I is evil.
I want. Is it this one?
What?
All right, I want you to try this one on your own. Go. Go. Okay.
Oh yeah, that is
William James, right? Are you meaning Williams?
Yeah.
Focus, please.
So after we move on, we want to integrate as in take the antiderivative.
Hmm? I'm gonna tell you, this is gonna be one where we're not gonna solve for y. Or you need to be careful if you solve for y. Because if we take this for root, what do you check? We have to have it
Plus or minus.
plus or minus.
I had
And this
it.
time we don't have a c input, so we would have to go plus or minus there. Which is why we don't tend to. But let's see, what type of stuff up there?
What do we do?
What do we do? That forms your
You know, y equals 2 and then
Okay. Pretty easy. Like how would I
Yes, that's
from
easy.
here, right? How would I move this to the other side? That's all you're doing. Well, then put it up on. Make it like y squared over.
Oh yeah, it is 1 squared.
Yeah, there you go.
And then that should be squared.
Correct, because then what would you have to do in order to solve for y? whenever we take the square root, what do we have to be careful about?
Plus or minus.
Correct. You have to have a plus or minus, and we don't have a c value in front this time, so you would have to have a plus or minus.
Okay, so.
So it looks like most people were able to do these first few steps.
What do we solve for?
So for our differential equation, we actually get a pretty straightforward differential equation. And I will go ahead and do it both ways depending on how you want to look at it. If I take the antiderivative, we get 1/2 y squared equals x squared plus c. Now, if you wanted to and you went ahead and solved for c, that is fine. Or solve for y, sorry. You would multiply both sides by 2, and 2c is still a constant, so it would still be c. And then this is the part where I said you have to be careful. Because when I take the square root of stuff, I have to put a plus or a minus. And there's not a c value in being multiplied in front this time. And there's not a way for us to put a c value being multiplied in front this time. So you would have to have a plus or minus. Now, the other thing, the other way that you would probably more likely see this written as, like as an answer, would be y squared divided by 2 minus x squared equals c. Because what type of equation is that?
Standard?
Standard
Or-
form of what?
I mean, it's like there's standard.
It's not an ellipse.
Circle.
It's not a circle. So for a circle, they would both have to be. It is a conic section, yes. So circles and ellipses both have what operation in between?
What?
Addition. Which one has subtraction? Hyperbolas. That would be the equation of a hyperbola. You didn't think you were gonna have to think about those ever again, did you? Remember, it's like the two in this case, since my y is first, it would be the two parabolas that are facing away from each other.
Oh, okay. It's that.
Kind of. Alright, what questions do we have there? Alright, we have one last one that I want to look at. And this one, I do want to add in an initial condition. It's really not as scary as it looks.
Always when there's e's, I have to go.
Whoa.
But remember, we like e's, because what's the antiderivative of e to something? No. Remember, we like e's because the derivative of e to the x is just
Oh,
e to
oh,
the
yeah.
x. And the antiderivative of e to the x is just e to the x. So when we're doing integration and differential equations, e's actually end up making our lives easier.
Wait, but I thought you always got multiplied by like whatever was on top.
The separate would be one.
E always got multiplied.
Because I remember like you would take like the derivative of.
Oh, we'll
each
get
of
there.
these.
Yes, I'm just saying if we have e to the x. Yes.
Okay,
We're not too
just
sensitive.
Subtract x1.
Alright. First up. Do I have a dy dx?
Yes.
We do. They're just not being divided, which is okay. Okay. That means that we would have had to do implicit differentiation to get here, which is fine. It's still a valid differential equation because they still have derivatives in it. Okay. But I still need to separate those two things to different sides. The only difference is this time, does it make sense for me to multiply by a dy?
No.
No. What would we want to do instead?
Subtract.
Yeah, we're just going to subtract the whole expression that has a dx with it. So it's already looking better, right? Okay, then we need to match up our corresponding variables. Do I have stuff on the wrong side right now?
Yes.
Yes.
Yeah. So what are we going to do first? Cool. And we will also need to divide by a
Why?
cool. So I get y squared minus 1 divided by y dy equals negative x divided by e to the negative x squared dx. Can we clean up either one of those? Alright.
Sure.
You can simplify the y squared minus 1 over
what's y squared over y?
Just y.
Yeah, so we get y minus 1 over y dy. Yes? Are we all okay with that? Alright, and then also, can we simplify the right hand side?
E negative x squared as e to the negative 2x. Could we just bring it to the equal x squared?
Yeah, so if I just bring it to the top, right? Because I have a negative in the bottom, right? So negative just means that I move it. Yes? So if I'm moving it, then that means we're moving it to the top. So it becomes positive. Yes? Can I take the antiderivative now? Yes. You should be able to. What's the antiderivative of y?
1/2 y squared.
Cool. Y squared over 2 minus, what's the antiderivative of 1 over y?
Natural log 1.
Almost.
Absolute right.
There we go. Now, on the next one, we talked about, do we know what the antiderivative of e to the x is? It's just e to the x. Well, right now, do we just have an x in there? How might I make it just one thing in there? Well, we're going to do a u sub. So u equals what? X squared. So then what is du? 2x dx, which is helpful because what do we have? An x. Okay, we don't have a 2 though. So we do need to get rid of that. So our integral becomes, I still technically have a negative, right? So it's going to be a negative 1/2 integral of what? E to the u du. What is the antiderivative of that? E to the u plus c. What was our u?
X squared.
Yeah, so we're just gonna plug that back in. Yes? So that would be our what? With the c in it.
Final solution?
Huh?
Final solution?
No, not necessarily. General solution, yes? Are we okay with that? That is our general solution, but this time I gave you an initial condition. Yes? So what do we want to do with that initial condition then? Find C. But, pretty straightforward. Let's come over here. I'll use a different color. So what am I plugging in for y? 1. So I have 1 squared is what? 1. So I should get 1/2. What is the natural log of 1? 0. Then I have a negative 1/2 times e to the, what am I plugging in for x? 0. What is e to the 0?
1.
Just 1. Okay, so then how would we solve for c?
Move everything over to one side.
Correct. So like, here, I'll simplify it first. I have 1/2 minus 0 is just 1/2. Here we just have a negative 1/2 plus c. So what does c equal?
0.
Not
2.
0.
Wait, 1.
It equals 1. So is that my answer?
No.
What do we need to do with that?
Put it in equation.
Put it in my equation. And this is also one where we would not solve for y. You don't even want to try to solve for y on this one. Would not be a fun time. So that is our final answer. See? That wasn't quite as bad as we thought.
Oh, it's
Yeah. What questions do we have there? We didn't even have to do any funky log rules or anything like that.
so do a bunch of funky other stuff.
What happened to, so when you did u sub, what happened to that negative x into the d?
It got scooped up by my du. So my negative's still there, right?
Mm-hmm.
Because my negative would still be here.
Oh, okay.
But my x dx was a part of my du. So this x dx now became a part of my du.
Okay.
Does that make sense? Yes. Which is helpful because we don't know how to integrate x e to the too much stuff. So we needed the x to get scooped up by our u.